The digital age, an era defined by the ubiquitous presence of computers, stands at the cusp of a paradigm shift. This revolution is fueled by the emergence of quantum computing, a fundamentally different approach to processing information than the classical computing that has powered our world for decades. To understand this impending sea change, we must first delve into the heart of both classical and quantum computing, unraveling their inner workings and exploring the potential consequences of their intertwined destinies. For over half a century, classical computers have served as our tireless workhorses, crunching numbers, processing data, and enabling countless technological marvels. From smartphones to supercomputers, these machines rely on the same basic principles, manipulating bits, represented as zeros and ones, to perform calculations and execute instructions. However, as we push the boundaries of computation, demanding faster processing speeds and the ability to tackle increasingly complex problems, the limitations of classical computing become apparent. This is where quantum computing emerges, not as a replacement but as a powerful complement to its classical counterpart. By harnessing the mind-bending principles of quantum mechanics, quantum computing opens up a realm of possibilities that were once relegated to the realm of science fiction. But before we dive into this exciting new frontier, let's take a closer look at the foundations upon which our current digital world is built: classical computing. At its core, classical computing is elegantly simple, relying on the binary system, a language of zeros and ones, to represent and process information. These binary digits, known as bits, serve as the building blocks of the digital world. Imagine a light switch that can be either on or off, representing a 1 or a 0, respectively. This simple concept forms the basis of classical computing. Transistors, microscopic switches within a computer chip, control the flow of electricity, flipping between these two states to represent bits. These bits are then organized into groups, typically bytes, 8 bits, to represent more complex information such as letters, numbers, and symbols. Just as the alphabet allows us to combine letters to form words and sentences, computers use combinations of bits to store and process data. This information is manipulated and transformed through a series of logical operations performed by the computer's central processing unit, or CPU. By following a set of instructions, the CPU fetches data from memory, processes it, and sends the results back to be stored. This cycle of fetching, processing, and storing repeats continuously, enabling computers to perform a wide array of tasks. While the binary system may seem limiting at first glance, its simplicity is the key to its power. By breaking down information into its most basic form, a series of zeros and ones, classical computers can process data with incredible speed and accuracy. Think of it like building with Lego bricks. Each brick, like a bit, is simple on its own, but by combining them in countless ways, we can create structures of astonishing complexity. Similarly, by stringing together bits, computers can represent and manipulate vast amounts of information. This information can take many forms: numbers, text, images, audio, video, and more. Each type of data is ultimately represented as a unique sequence of bits. For example, the letter A is represented by the binary code 01000001, while the number 10 is represented by 00001010. The ability to represent and manipulate data in this way is what enables computers to perform a wide range of tasks, from simple calculations to complex simulations. However, as we push the boundaries of computation, demanding faster processing speeds and the ability to tackle increasingly complex problems, the limitations of classical computing become apparent. Quantum computing, in stark contrast to its classical counterpart, delves into the enigmatic realm of quantum mechanics, a branch of physics that governs the behavior of matter at the atomic and subatomic levels. While classical computers rely on the deterministic nature of bits, quantum computers embrace the strange and counterintuitive world of quantum bits, or qubits. Unlike classical bits, which can only exist in one state at a time, either 0 or 1, qubits leverage the principles of superposition and entanglement to exist in a combination of states simultaneously. Imagine a coin spinning in the air, not yet settled as heads or tails. This indeterminate state, where the coin embodies both possibilities at once, provides a glimpse into the essence of superposition. Entanglement, on the other hand, links two or more qubits together in a profoundly interconnected way. When two qubits are entangled, their fates are intertwined, regardless of the distance separating them. Measuring the state of one entangled qubit instantly determines the state of its partner, even if they are light years apart. Section 5. Superposition and Entanglement, the quantum dynamic duo. Superposition and entanglement, the cornerstones of quantum computing, empower quantum computers with capabilities far exceeding those of classical machines. These quantum phenomena enable qubits to explore a vast computational space, exponentially larger than that accessible to classical bits. To grasp the power of superposition, consider a classical computer attempting to find a specific grain of sand on a beach. It would have to examine each grain individually, a tedious and time-consuming process. A quantum computer, leveraging superposition, could examine all grains simultaneously, dramatically accelerating the search. Entanglement, on the other hand, allows for the creation of complex correlations between qubits, enabling the representation and manipulation of information in ways that are impossible for classical computers. This interconnectedness empowers quantum computers to tackle problems that are intractable for even the most powerful classical supercomputers. These unique quantum properties hold the key to unlocking unprecedented computational power, enabling us to address challenges that have long remained beyond our reach. However, harnessing the power of superposition and entanglement is a formidable task, fraught with technical challenges that researchers are actively working to overcome. Section 6. Quantum versus classical, a head-to-head comparison. While quantum computers hold immense promise, it's important to understand that they are not meant to replace classical computers entirely. Instead, they excel in specific areas where classical computers struggle. Classical computers are masters of everyday tasks, from browsing the internet to running productivity software. They excel at processing large amounts of data in a linear fashion, making them ideal for tasks like word processing, spreadsheets, and video streaming. Quantum computers, on the other hand, are better suited for tackling problems that involve complex calculations and simulations, such as drug discovery and materials science, simulating molecular interactions to design new drugs and materials, optimization problems, finding the optimal solution among a vast number of possibilities, such as optimizing traffic flow in a city or supply chain logistics, cryptography, breaking existing encryption algorithms, and developing new, more secure ones. The table below summarizes the key differences between classical and quantum computing. Section 7. Quantum leaps, real-world applications. Despite being in its early stages of development, quantum computing is already making its mark in various fields. Let's explore some compelling real-world applications. Medicine quantum computers can revolutionize drug discovery by simulating molecular interactions with unprecedented accuracy, accelerating the development of new treatments for diseases like cancer and Alzheimer's. Materials science. By simulating the behavior of materials at the atomic level, quantum computers can aid in designing new materials with enhanced properties, such as stronger and lighter alloys for aircraft or more efficient solar panels. Finance quantum computers can optimize investment strategies, manage risk more effectively, and detect fraudulent transactions with greater precision. Section 8. The Quantum Horizon Challenges and Opportunities. The path to realizing the full potential of quantum computing is paved with challenges. Building stable qubits. Qubits are extremely fragile and susceptible to environmental noise, making it challenging to maintain their quantum states for extended periods. Scaling up quantum computers. Building quantum computers with a sufficient number of qubits to tackle complex problems remains a significant hurdle. Developing quantum algorithms. New algorithms specifically designed to leverage the power of quantum computers are crucial for solving real-world problems. Despite these challenges, the future of quantum computing is bright. As research progresses and technology matures, we can expect to see significant breakthroughs in the coming years. Section 9. Conclusion, a future intertwined. Quantum computing is not merely an incremental step in computational power, but a profound leap that promises to reshape the technological landscape. While it may not replace classical computing entirely, it will undoubtedly augment and complement it, ushering in an era of unprecedented computational capabilities. The future of computing will likely involve a hybrid approach, where classical and quantum computers collaborate to solve problems in a synergistic manner. Classical computers will continue to excel at everyday tasks, while quantum computers will tackle complex problems that are currently intractable, driving innovation across a wide range of industries. As we venture further into the uncharted territory of quantum computing, one thing is certain: the journey will be filled with exciting discoveries, groundbreaking innovations, and a profound transformation of the world as we know it.